Hi. Hi. As you already know, I'm Michaela, and I'm here to talk about WebVR. Reading the topic of my talk, you might have thought, web in 3D? Isn't that nonsense? Isn't thinking and talking about a virtual reality web nothing more than ridiculous? And most of all, should I even care about WebVR? Well, you might have guessed already, I'm here to tell you that you should care about WebVR. Even if you're not a gamer, even if you're just not into virtual reality, or even if virtual reality makes you sick. Why, you ask? Because if this technology is permanent, and at the moment it looks like it is, because virtual reality will have a great impact on our users. And we all agree that we should care about our users, hopefully. This is why I will tell you today the most important facts you have to know as developers about WebVR and VR to create responsible virtual reality experiences. I'll begin with some brief information about the hardware and VR concepts, and then we'll have a look into the WebVR API. And afterwards, I'll come to the topic I'm most passionate about, a good user experience in WebVR applications. Before I forget, you can all download the slides with all the code and links. I will give you the URL at the end of the talk. So, since we only have 30 minutes, I won't talk about what virtual reality is. And I also won't talk about why I think virtual reality matters. Instead, I want to concentrate on the things we as developers have to know when we want to create a virtual reality application. So let's begin with a look at the hardware. First, there are mobile VR devices, which are basically smartphones and relatively cheap headsets with magnifying lenses. The input methods on these devices vary. We have, for example, on the left, the Google Cardboard, which has only one button on the side. And there's the Samsung Gear VR, which has a button and a touchpad on the side. And on the right, you see the newest one, the Google Daydream View, which comes with a special VR controller with 3 buttons and a touchpad and volume controls. There are also desktop VR devices. They are significantly more expensive because they also contain the sensors and the screens. The computing power comes from the desktop computer or the gaming console to which the VR device is plugged. The input method of these devices also vary. The Oculus Rift users can use Oculus Touch motion track controllers, and also the HTC Vive ships with Steam VR motion track controllers. On the right, you see the PlayStation VR. You can use with the PlayStation Move controllers. There are also standalone VR devices in theory, which contain not only the sensors, lenses, and screens, but also the computing power. At the moment, this is only theory because there are no really important devices on the market right now. But of course there will be, because this may be the most convenient form to use virtual reality applications without any plugs and cables, but a higher computing power than a smartphone. So now, as developers, we need to know about the different hardware and VR concepts when we want to not exclude users. So let's talk about the most important concepts of virtual reality: stereoscopic images and tracking. We'll begin with stereoscopic images. When we talk about stereoscopic images in the context of WebVR, we are talking about 2 images next to each other showing the same content, but from a slightly different point of view. The offset between both images is called IPD, which means interpupillary distance. By showing these images to our eyes, we are exactly recreating how we see the world naturally, and our brain combines these images like it always does and gives us the perception of 3D depth. When we are looking at WebVR images, we often see not full-screen images like these, but some kind of distorted images like this. We need this effect to compensate the distortion the thick lenses are making to the images. If we wouldn't have this distortion, the images would be distorted like this on the right. But if we apply a contrasting distortion to the original image, the images behind the lenses will be without any distortion again. So, by showing these slightly different images to our eyes, we are already getting the perception of depth. Now, to make our brain believe we are actually in this virtual world, we have to include tracking. All VR devices I've shown include 3 degrees of freedom tracking sensors for the rotation around the 3-axis. More advanced VR devices, for example, like the HTC Vive, also include tracking for the position of the user in a room, which is called room scale VR. You can surely imagine that the more tracking sensors we have, the more intensive is the feeling of actually being in a virtual world. This immersive feeling gets even stronger if we include input controllers with rotation or position tracking sensors. Now, how do we create such applications in JavaScript? Let me show you the stack we'll be working with. First of all, there's, of course, the browser. Then, with WebGL, we have an API for rendering GPU-accelerated 3D graphics in the browser. We heard about this morning in Jess's awesome talk. Now, we need to get access to the head-mounted display and the sensors, and therefore, we have the experimental API WebVR. On top of this, there may be further JavaScript libraries. One common library to reduce the effort of writing WebGL is Free.js. Now, let me show you this technique in a simple example. Here we have an obviously distorted 3D spherical video, which I recorded with my 360-degree camera. What we want to do is play this spherical video undistorted and in a stereoscopic way. Also, we want to use the rotation sensors of the devices to let the user look around while the video is playing. So our setup could look like this. We have a 3-dimensional coordinate system where the camera is the user. Around the user, we will create a large sphere, which will be our video canvas. So a simplified version of this code could look like this. Everybody who is familiar with WebGL or Free.js see nothing new here. First, we create a scene and the camera. Then we create the sphere with the video texture. And then we render it all to the canvas within the render loop. This is only WebGL or Free.js. There's no WebVR here at the moment. So how do we render this scene not on the default screen on the canvas, but on the head-mounted display? This is where the WebVR API comes into play. First, we need to get access to the VR device. Therefore, we use the navigator interface extension, getVRDisplays. It returns a promise that resolves in an array of VR display objects. And one VR display object represents one VR device, which holds then information about the VR device. For example, if the device is currently connected, if it is presenting, and it also has methods like get eye parameters, get pose, request present, submit frame, and request animation frame. We can then use the VR display object to render content to the head-mounted display by using the request present method. Request present takes an array of VR layer objects which have a property source containing the HTML5 canvas we use to draw on. The cool thing is about request present is that it handles device-specific rendering issues, like, for example, the barrel distortion I've talked about. So you don't have to implement this stuff manually. And another cool thing is that, another thing you have to know is, which is not so cool, obviously, for security reasons, this request present method only may be triggered by a user action. You may compare request present then to request full screen. It also requires a user action, and request present first requests that the VR device goes full screen. So you would probably write something like this. Request present also returns a promise that is fulfilled when the presentation has begun. And this is then the time we can start the render loop by using VR display's request animation frame method. VR display's request animation frame is equivalent to Windows request animation frame, but it has device-specific features for rendering on a head-mounted display. It also draws continuously on the canvas, but it does this in a higher frame rate, depending on the VR device, not with 60 frames per second, but with 90 or even 120 frames per second. Within the render loop, we are first scheduling our next frame's callback, and then we can update our scene and camera position and rotation, depending on the VR display's tracking sensors. Therefore, we have different interfaces. There is, for example, the getPose method, which returns a VR pose with lots of information of the sensors at the moment. For example, there's the user's orientation, which returns a quaternion, or the user's position, which returns a 3D vector. The mobile VR devices will return for a position null because, like I said before, it has no sensors to know where a user is in the room. Now we have to render our scene twice in a stereoscopic way, and this is where we can use the getIParameters method. It gives us all the information we need if we pass one string for each eye as an argument. So there's the offset, which is 1/2 of the interpupillary distance, or the render height and width, which returns the recommended width and height of a canvas for each eye. With this information, we can update our cameras and scene and render it all to the canvas by using the submit frame method. And this is basically all you have to know and to do to get our video playing and updating while the user changes her pose. So now, let's get back to the stack, because I want to give you also some practical tips about the libraries we used to create this prototype. We didn't use A-Frame, but we used Free.js. So you might have already guessed it. You are right, WebVR, the API isn't ready today. There's a good website called iswebvrready.org, where you can see the current implementation status of the API. So fortunately, as long as the API isn't shipped with our modern browsers, we can use the WebVR polyfill. And there are some small but really useful libraries that add support for the VR controls and the stereoscopic rendering to Free.js. Last but not least, we used the WebVR Manager from the WebVR boilerplate by Boris Smooth from Google, which adds some basic cross-browser support. Okay, talking about cross-browser support. In a perfect world, our prototype would work within every browser, but of course with less features in older browsers. So, for example, a browser not capable of WebGL would get a static image, and a browser capable of WebGL would get a 3D WebGL application that works with the mouse or the keyboard. Then, on mobile devices, We want to make use of the touch input, and more importantly, the gyroscope, to create a more engaging application. And of course, a browser capable of WebVR gets the full WebVR application with all the WebVR features. One issue with WebGL and WebVR apps is definitely the long loading time. We have large textures, images, videos, 3D models, so you want to include mechanisms like progressive loading in your application. Now, as you've seen here, we not only use the WebVR API, but also the WebGL API to create this prototype. And let me tell you, you'll be using more APIs to create a full WebVR application. First of all, there's the Gamepad API. This has already shipped in modern browsers, but it will get more features for handling VR-specific gamepads, like, for example, the gamepad hand method to discover in which hand the gamepad lies, or the gamepad pose interface to get the orientation, velocity, position, and acceleration of the gamepad. Then there's also the Web Audio API we can use to create and add spatial sound to our application. And the last API I want to mention is the Web Speech API you can use to avoid the very uncomfortable way of typing into a keyboard in VR. Well, because I think we can all agree that typing into a keyboard with a headset on, or even worse, I find it even worse, clicking single keys with a pointer on a digital keyboard is not the best way to make text input in VR. These are only two examples, but I think overall we should talk about user experience design in VR application, because the way users interact with the digital world changes dramatically in VR. Bo Cronin, I hope I spell his name right, Bo Cronin has created this hierarchy of needs in virtual reality, which I find very compelling and a good guideline to prioritize our focus when we are creating VR apps. So the hierarchy shows that the most important needs in VR are first comfort and interpretability. And only afterwards comes usefulness and delightness of an application. So comfort means that a user can use your application without feeling unwell. And interpretability means that the virtual world feels convincing to the user. If these both needs are satisfied, the user will get the feeling of actually being present in this virtual world. And this is what we want to achieve. So we cannot talk about all needs. This is why I will focus on comfort and begin with some basic facts about ergonomics. Our VR application does not have a limited viewport. On the contrary, we have an infinite canvas, and the user has only a limited field of view. This field of view may change because a user can rotate her head and look around. So some smart people found out how big this field of view actually is. If a user is sitting, she can see a 70-degree circle in front of her. And then, with turning the head to each side, comfortably around 30 degrees, or with stretching max 80 degrees, the range increases to 230 degrees. Of course, we could turn around and bend much more, but this means your main content should be within this range if you want to have your user engaging with it without effort. One other thing you have to remember is that we have the best depth experience if the content is not more than 20 meters away and not closer than half a meter. So everything closer than 50 centimeters will make us cross-eyed, and you don't want this. Since the devices at the moment have a relatively low amount of pixels per degree, we also have to use large font sizes. Most designers agree that it should be over 20 pixels. One word about PPD, which means pixel per degree. The devices at the moment have around 10 PPD. And a good resolution to not see any pixels anymore would be 60 pixels per degree. So this is then the time you can stop worrying about anti-aliasing and use smaller font sizes. Now, we know where to put our content to make it comfortably visible for the user. What can we do more to make our users comfortable? We can avoid eye strain by using darker colors. And we can avoid focusing on different depths. We can also avoid creating environments that may trigger phobias, like large empty rooms or rooms where you're standing on a stage. Or small rooms, messy spaces, heights, and underwater environments, for example. Also, we should use correct scales, and we do not want to move things fast towards the camera, especially sharp or dangerous or pointy things. Also, we do not want to attach things to or near the camera, so head-up displays are not a good idea. Then, now, what about the elephant in the room when we talk about virtual reality and comfort? What about simulation sickness? Making a user sick, causing him or her physical pain, or making him or her even throw up is hopefully the last thing you want to do as a developer. Now, what can we do to avoid simulation sickness? Simulation sickness occurs, oh, it's really dark. Simulation sickness occurs when our sensory inputs are not consistent, which means, for example, when the simulation tells us we are in a car race and we are actually just sitting still in a room. There are some best practices to avoid simulation sickness. First of all, don't use acceleration. Then don't move the horizon and do not force movement on the user, which means do not move the camera. If you want to create animated scenes, you should allow additional head movement. So, for example, put the camera on a dolly and then animate the dolly. Also, keep always head tracking and watch out for a low latency and a high frame rate. Avoid flicker and blur because they indicate movement, and you may consider adding a stable focus point. Your application should support short usage, so save states or make it offline capable. And consider using more abstract patterns than realistic ones. For example, flying cartoon hands will work better than realistic arms and hands. Or another example is that a walking simulator will make more people sick than a flying spaceship simulator. This is because we know really good how walking should feel like, and a slight difference can make our brain confused and the user feel unwell. Yeah, we could talk about this all day, but time's flying by, and we want to get back to the web and VR. We are in a kind of similar situation like in 2007 or 2008, when the iPhone and with it the first mobile sites appeared. Back then, we had to reconsider how we present our content on a small screen or on screens with various sizes and ratios. And now, we have to think about how we present our content when there's no more separation between the user and the application. Our users are finally in our applications. So at our company, we try to get insights about this by using the example of a simple image gallery. How would an image gallery look like if the user was in the application? I think that the VR web comes hand in hand with losing our UX design metaphors, because we all agreed that an image gallery, of course, would be a gallery with images in it. So this is our application. A user can look around and move and see all the images. Try it. It's a prototype, but you can try it. I will give you the URL also at the end of the talk. Okay, let me ask you one last question. What about the future? At the moment, there are some smart people developing the API, and they are also thinking about making the VR web usable without WebGL and JavaScript, but only with HTML and CSS. For example, we could think about making our websites visible in a 3D space and let the developer decide with CSS how the spherical image around the user should look like. Or, like A-Frame does it, we could think about tags for 3D graphics that contain also the textures and the animations. Or what about media queries for VR user agents? There are no actual proposals at the moment for these mechanisms, but I think we should keep in mind that the VR web is not uniquely defined yet, and you all can be part of shaping it. So, if you like it or not, as a developer or a designer, you are at least partly responsible for the well-being of your users. And with a VR web, you might not be responsible only for a low battery or high telephony costs anymore. With a VR web, you could cause, like I said, actual physical and psychological pain to the user. We talked about throwing up. We could also imagine like running into walls or falling, which is also what I was afraid to come here on stage when I think about it. But let's be serious. Even worse, we could trigger paranoias and not prevent that scary or abusive material appears directly in front of a user's eye. This is all way more serious in 3D, where we try to make our users think that they are in another world, and then this world is violent and hurts them. So there's a study I read about, and that lets people in VR be a superhero, and then put these people and other people in a situation where someone needed help picking up dropped pencils. And the people who were a superhero in VR actually helped more often and faster than the others. So you see that your content and how it is presented matters. And this is why you all matter. So be responsible and be aware of this. Yeah, I have many resources for you in the slides and also a list with interesting people you could follow if you're interested in WebVR. And this is the URL to the slides and the prototype. And there's also a newsletter about WebVR. If you like, subscribe to it. That's all. Thank you.